Okay, it's our last day before break. Let me share a couple things with you here. Okay, so first off, in the let me get a new screen. All right, so the study guide, you should be able to complete that here over break or before we get back. And then we'll have a quiz on some topics on chapter 5 after break, along with some other stuff that we'll do about coral and coral propagation that I mentioned. All right, so in the plan for the week for yesterday and today, there's the Zoom recording from yesterday, and then the Ever Given is free. The Suez Canal is completely open. They're trying to get all the ships through and whatnot. So that's all kind of getting cleared up. The hold on a second, I got some feedback. I'm just gonna hit mute, but you can turn yourself on if you need to, like turn your mic on. Let's see, mute all. Okay, and then in for today, I want to say a couple things about uh, resilience for freshwater and saltwater fish for changes in water chemistry over the course of a year and how that affects keeping fish in aquariums and whatnot. But the last page of the study guide has some questions about some topics that are on pages 167 and 168. And yesterday I mentioned that I'd have a PDF available for that. So these are just pages 167 and 168 of your textbook that describe a couple useful things. On page, it should come up nice. This will be in full color. It's a PDF. One about solubility and amounts of carbon dioxide in the ocean and how carbon dioxide concentration varies with depth. Um, and then on the bottom of that page, and then on the next page, about solubility and distribution of oxygen in the ocean. So it turns out that gases are more soluble whenever the liquids that they're dissolved in are cold. And so places in the world's ocean where there's very cold water, you tend to get higher concentrations of oxygen and carbon dioxide. But this chart here shows about what percent of the different gases that exist on our planet are in the ocean or in the atmosphere. And it turns out that of all the nitrogen gas that's on the earth, the vast majority of it is in the atmosphere. And it turns out that the atmosphere is the air you're breathing right now is about 78% nitrogen, about 21% oxygen, and very, very, very little carbon dioxide. So the gaseous atmosphere is mostly composed of nitrogen, has some oxygen. When you look at gases that are dissolved in seawater, um, like the ocean has different gases dissolved in it, and there's less nitrogen dissolved in seawater. There's more oxygen dissolved in seawater than comparison to the atmosphere, but there's much greater carbon dioxide dissolved in the ocean. Carbon dioxide enters the atmosphere through like combustion processes and burning. There are a few natural processes like the outgassing from volcanoes and carbon dioxide production in respiration by plants and animals. But the ocean is far more able to dissolve carbon dioxide than the atmosphere. So when you put carbon dioxide in the atmosphere, it doesn't just stay in the atmosphere; it can go into the ocean. And this shows concentration in parts per million by mass in the ocean. So even though carbon dioxide is in relatively low concentration in the ocean, it has a much higher formula mass than that for oxygen and nitrogen. Anyway, and then there's things about students asking, and a question I put in the study guide about increases in carbon dioxide in the ocean and in the atmosphere, and their effects. So there are some effects that you read about related to carbon dioxide in the atmosphere as compared to carbon dioxide in the ocean, and what effects that has on changes in the climate and changes in the ability for animals to be able to survive. So anyway, those couple questions that I put in the study guide that are about um, topics on pages 167 and 168, those are now in the folder. I put them not only straight up in the chapter 5 folder, So it says at the bottom, it just says pages 167 and 168.pdf, but also in the plan for the week, it says here's a PDF 167, 168. Click that link, it takes you to the same page. All right, so that's available too. The other thing I wanted to mention is about how fish and mollusks and plants and all kinds of animals that live within aquatic systems, whether it's in the ocean or whether it's uh, in rivers or lakes and whatnot, have to be able to survive in varying conditions. So it turns out that water has a huge heat capacity. It has a very high resistance to changes in temperature. So if we pick somewhere, I don't know, maybe like off the coast of Long Island. So here's New York City, and Long Island extends out into the Atlantic Ocean. And you have all this water maybe south of Long Island. In the wintertime, the water cools down, and in the summertime, the water warms up. So there are annual changes in temperature for the water in the ocean. But this ocean is incredibly massive. The water is very deep. There's constant delivery of water by currents. So what we find is that over the course of a year, especially even over the course of a day or even weeks or months, the temperature doesn't change very much, the pH doesn't change very much, the oxygen concentration doesn't change very much in big open ocean water. So fish that live out in the open ocean, uh, they don't experience huge changes in temperature and pH so much like fish that are inland. And if anything, if you're a fish that's in the ocean and the water happens to be too warm, you can easily swim to somewhere where the water's cooler in a relatively short period of time as compared to the time that it takes for the temperature of the ocean to change in your location. The only exception to this is sometimes in inlets and bays there can be a huge fish population, and then on a hot summer day the temperature may increase dramatically, and that causes the oxygen concentration to come down, and you can end up with fish kills as a result of those big changes, but happen in isolated locations like in small inlets and small bays. In comparison, whenever you consider a body of water that's inland, like if we think about the Susquehanna River here in Williamsport. So here's the high school is like, where did we go? The high school is like right here. So just south of us from the high school, across 220, there's the Susquehanna River. And the deal with the river is that in the summertime, the water will warm up and it'll be nice, and you can swim in it and go tubing and um, water skiing and whatnot. The water is reasonably warm. It's okay to get into. And then in the wintertime, it's ridiculously cold. It'll get to the freezing point and it can ice over. Some years we get a whole lot of ice on the river. Other years we get a whole lot less ice on the river. Sometimes ice flows. So the thing is that fish have to be able to put up with those changes in temperature from nice warm water that you can swim in to freezing cold water in the wintertime. Those kind of differences in temperature just don't happen in the ocean. Similarly, you could have a nice warm day where maybe we've experienced some drought and the river is nice and shallow, and the water's kind of all backed up behind the dam. The water's gotten to be nice and warm and whatnot, and maybe it hasn't rained very much for the last couple weeks. And then all of a sudden, you get a heavy rainstorm, and that heavy rainstorm washes cold water, because rain's usually fairly cool, massive amounts of cool water into the river, causes the flow of the river to increase. The temperature of the river can drop in a short period of time. The amount of sediment and debris increases dramatically and really fast. So here's a for instance. This is from, well, this is kind of old. I just randomly searched a year, but the United States Geologic Survey has information and data that goes way back in the day for water quality in rivers and streams all throughout the nation, and sometimes other places in the world. So this says USGS West Branch of the Susquehanna River at Williamsport, Pennsylvania, and it has the latitude, longitude, the drainage area. So this is how much square area of land where precipitation falls on, where the water flows past Williamsport. So basically 5,682 square miles of land in Pennsylvania has its water drainage come past Williamsport. This is our altitude above sea level, which doesn't really make a whole lot of difference. But this is for the year 1982. You could do it for pretty much any year, and it's going to be very similar. And this has specific conductance. So this is how much the water conducts electricity. And in order for water to conduct electricity, you have to have an electrolyte in it or a salt in the water. And so throughout the year, you'll see that there's rapid or big differences in the salinity of the river. And so this is salt that's coming from land, maybe from limestone that's being dissolved. Could be even salt that's salt runoff that we have from putting salt on roads, all kinds of different effects. And you see that over the course of this year, are some months like April where the conductance, which is the relative amount of salt in the water, is low, 146. And then other months, like here in September, 393. So that's a dramatic difference in salinity. This is, 2.5 times greater salinity than in April. Where in the ocean, the difference so not only is the ocean water significantly saltier than the water on land, but the ocean water doesn't change in salinity hardly at all. Definitely doesn't, triple over the course of just a couple months. Also, I picked one that didn't have many months. Anyway, this is a temperature chart over the course of a springtime. So here you've got a temperature in Celsius of 17.7, and then by July the temperature is warmed up to 24. So that's an increase in temperature of like about 7 degrees Celsius or about 14 degrees Fahrenheit. That's a dramatic difference in temperature for the river temperature. And in fact, this 17 from May to 24 in July, I'd bet that back here in January, the temperature might have been, 5 or even 0 Celsius, right at the freezing point. This shows differences in pH throughout the year, and differences in pH come about as a result of the water being more acidic or less acidic. So rainfall is slightly acidic, so you'd expect a lower pH in months with higher rainfall amounts, which for us here in Williamsport is more common in the summertime. So here in the months of April, May, and June, we have the lowest pH because rain is slightly acidic. And then the carbon dioxide concentration also affects the pH. And then if you get high amounts of runoff, that can help buffer the water and raise the pH. So the pH of the water in the river can range in this year from as low as 6.68 to as high as 7.29. And 1 on the pH scale actually represents 10 times more acid. So if you went from a pH of 6 to a pH of 7, like rate at 6 to rate at 7, that actually represents a 10 times increase in the amount of, or 10 times decrease in the amount of acid that happens to be in the water. In other words, pH of 6 is 10 times more acidic than a pH of 7 because it's a logarithmic scale. So in that question in the review that's about, why can't saltwater fish deal with big changes in temperature, big changes in pH, big changes in salt? A big deal is that the ocean is very stable in its temperature and its pH. You measured in the water chemistry lab that water has a very high resistance to changes in pH, and the ocean doesn't change its salinity very much. Where in freshwater, in rivers and lakes, you can get huge changes in pH, temperature, amount of stuff that's dissolved in the water, even in very, very short periods of time. So then as an effect, whenever we keep fish in aquariums, if you're trying to make a freshwater aquarium, it's a lot more forgiving in the sense that when the fish go in the water, not to say they don't care what the temperature is, but freshwater fish can generally tolerate a much bigger range in temperature, a much bigger range in pH. You don't really put much salt in the water anyway. So keeping freshwater fish in that sense is a little bit simpler. Our challenge with keeping saltwater aquariums, not only like a home aquarium, but here where we do some research or even a big public aquarium, is to maintain the water quality as stable as you can, because the fish that come from tropical coral reefs or other areas of the ocean where the water doesn't change by very much have not adapted to those changes. And as a result, if they experience big changes in pH or temperature or oxygen concentration or salinity, it can be detrimental to their health. They may stop feeding. It could encourage You know, parasite development, that with parasites that happen to be on and in and around the fish due to stress. And so another reason why people sometimes say that, you know, keeping saltwater aquariums is more difficult, which is sort of a myth but has some truth to it, is that what we really care about is massive amounts of stability within the water, to keep the water temperature very constant, keep the pH nearly constant, keep the salinity as constant as possible. So we have a lot of control systems that exist in the fish room in order to do exactly that. We're trying to keep the temperature, you know, within half a degree Fahrenheit each day, not have changes in pH, not have changes in salinity, try to keep the calcium always about the same level. So the water testing you did in the water chemistry lab is a, a very critical part of helping to maintain the quality of the water in saltwater aquariums. Anyway, if you're interested in seeing more about water quality, especially like if you're into fishing and you enjoy, you know, going trout fishing or bass fishing or whatever like that, a lot of fishermen talk a lot about, you know, water quality and water conditions and how it affects, uh, you know, the probability of fish to want to bite on a certain day. If you go to usgs.gov, or especially waterdata.usgs.gov, you can search for particular places. You can also just simply get there by, if you just search. So usually what I do is just search like water temperature Susquehanna Williamsport. Or if you're interested in, you know, Pine Creek, you can say like water temperature Pine Creek, and then, or maybe how about the Lycoming Creek? So you can be like Lycoming Creek, because there's going to be a bunch of Pine Creeks anywhere, anywhere, or people say Pine Creek. So water temperature Lycoming Creek, you can click water temperature Lycoming Creek, and it'll take you to a page that'll have real time data. So this will be real time water levels and real time temperature information. So here you can say I want to know the gauge height. This only has water levels, which affects, you know, whether or not fish are going to bite. But for major bodies of water like rivers, there's more detailed information about water temperature, pH, and that's maintained by the United States Geologic Survey, USGS. They do stream forecasting and provide information about water quality to uh, environmental services agencies, you know, um, information for flood forecasting to the Flood Forecasting Center, stuff like that. So anyway, that's all I have for you. Uh, if you have any questions about anything, you can put them in the chat or turn on your mic and ask. Otherwise, hope you have a good break. And I don't have anything that you really need to worry too much about over break. And then when we come back, we'll do some stuff with coral, and then move on into some physical oceanography and biological oceanography stuff for like the remainder of the course. If you know anything else, I'll see you. Have a good break. If you got questions, put them in the chat or just turn on your mic and holler. Otherwise, see you in April.
See you, Flint.
See you, Mr. Flint.
Deuces.
Deuces, my guy.